So just as a little bit of a review here, we've been talking in this section, obviously, about radiometric dating. It is the title of the section, after all. So just to make sure we're all clear on how this process works, I want to go over it just one more time. So if you have an element and it's radioactive, again, what that means is that it's not stable. So the atoms, the molecules, everything that makes it up is going to be changing into another element that actually is stable. But this process of changing, or decaying as we call it in the science world, comes with a side effect, and that side effect is that a lot of potentially harmful energy can get released, and of course we know this as radiation. That's what causes all the bad things that go along with being around something that's radioactive. But it was this process of radioactivity where you've got one type of element, a radioactive element, decaying over time into a non-radioactive element, that if you can see the proportion of those two things, you should be able to ballpark an age for how long it's been decaying. So we looked at some examples of this yesterday, and this was one of those examples, Mount St. Helens here. And when we dated these different samples, again, we did it with the whole rock method. We also did it using individual minerals. And when we did that, we got kind of a spatter of data that's all over the place here. So just to give you an idea of how the scientific community deals with numbers like this, because, I mean, they have, imagine they come across a rock and we don't know when it was made. There was no lava dome that was documented to be made in 1984. To give us a year that we know how old it is. Yes?
How do they find out the age of like the thing never fully decays?
Well, I mean, it would, in the lab you can measure the decay rate over time, even if you haven't seen the whole thing decay. So, imagine, again, you come across a rock, you don't know the age, but being a part of the scientific community, you know how old it should be based on, naturalistic philosophy and the evolutionary story. So let's say this rock, we're going to forget it was made in 1984. Let's say that according to that philosophy, it should be 1.5 million years old. So here's what you do in the scientific community. You look at these results, and what you do is you publish this 1.7 million years old age. And you say evidence shows from this dating method that this rock is 1.7 or 1.5 million years old, and that matches up well with the history that we believe to be true. And what you do then is maybe you mention in a footnote this 900,000-year-old age, because it's not really that far off by comparison. But for all these other results, you'd chalk this up to contamination, you'd chalk this up to contamination, and you'd certainly chalk that up to contamination. So when you're publishing these results in the scientific community, you're really just picking out the ones that match up with that preconceived philosophy, that timeline that's already been accepted. And you can just see, using common sense, the trouble with this. But this is the methodology that got us the age of the Earth to be 4.5 billion years. Because you radiometrically date these rocks. The oldest rock on Earth that we date is 4.5 billion years old, based on this methodology. And so that's where that age comes from. When you Google how old the age of the Earth is, it'll say 4.543 or whatever that number is. And this is how they determine that. And of course, yesterday we went through and talked about the issues with that. Remember, there's 7 things that you have to assume. You have to assume that you know the starting conditions, that you know how much parent and daughter element were there at the start. You're assuming the decay rate has been constant the whole time. You're assuming no parent has been added to the system, assuming no parent has been subtracted from the system. You have to assume the same 2 things for the daughter element. And again, none of these assumptions are scientifically verifiable for rocks thought to be millions of years old, because nobody was there to cross-check those dates. There's no way for us to know if this methodology and if these assumptions are okay over the long term, because there's no way to go back in time to see that. And that's what that says. All right, so here's another another way that we can kind of explain how far off these numbers can be, because again, we're seeing these results and they come back as totally inaccurate and inconsistent. So why is that? Because we take very special care in ladies. You'll just have to keep it down a little bit because the camera picks that up too. So we take very special care to make sure there's very little contamination in these samples that we have undergo this process. But the thing is, remember the half-lives of the methods that we use to date things like the Earth or other things that are supposedly billions of years old have half-lives that are extremely, extremely long. So like the uranium-lead method is 4.5 billion years old for its half-life. Rubidium strontium is 50 billion years old. Samarium neodymium is 100 billion years. So it takes a long time for just half of that element to change into its daughter element. And if you have just the slightest amount of daughter that's contaminating that sample that you can't account for in your methodology, your numbers are going to be way off. You know, we use the potassium-argon method to date rocks and lava rocks and things like that. And that's the shortest of those time scales. So using that method, after 6,000 years, if just 1% of that argon is daughter, if 1% of it is contaminated, that would correspond automatically to an age of 18 million years. That's how far off your numbers can be just by having a slight bit of contamination from the corresponding daughter molecule. And even the tiniest amount of element yields an enormous age error. This error would be even larger for the other elemental methods because, again, their half-lives are much larger than this number right here, some even going into the 100 billion year range. And again, Drew had a great question, you know, how do we know for sure that these are true? Because you can't measure over that period of time. And the answer is, we don't know for sure. We can't measure over that period of time. It's a very good observation. But if you have very sensitive machines and you've got a giant block of potassium and you're observing it decay into argon, you can observe how quickly that change is taking place. So you don't need to observe the whole half-life to see this. You just need to, observe it very specifically over a short period of time. And that's where these numbers come from. But again, Drew's point is absolutely true. There's no way for us to know if these 7 assumptions that we have to make are consistent over those billions of years. And that's where the big issues come in. So the scientific community realizes there's lots of issues here. So they introduce one of the ways to sort of patch up this theory, and that's through the isochron method. So the question is this something that helps? So atoms of an unstable radioactive element, parent, transform into atoms of a stable non-radioactive element, daughter. That's what guys, thank you. That's what radiometric dating is based on. We've talked about this at length already. But in some cases, in addition to the daughter isotope, there's another naturally occurring stable isotope of the same element as the daughter. So not only does the parent give rise to the daughter, it also gives rise to a sister non-radioactive element. And so the idea here is the ratio of the daughter to sister and parent to sister can be plotted on a graph, and you can use that graph to figure out how old that sample is. And this is great because it makes no assumptions on what was present when a rock or mineral was formed. And even though there are still then 6 assumptions you have to assume are true, anytime you're using less assumptions, the better off it generally is. So that's one less assumption. How well does it work? So again, these were the results we got when we dated the rock of known age from Mount Naruhoe in New Zealand. So let's just take a quick second, review these numbers, and then we're going to do the same thing with the isochron method and see if it improves things. So we've got several 100,000 years up to about 3.5 million. So let's see what happens with the isochron method. Same lava flow from the same mountain, and when we use these methodologies in order to date them with the isochron method, we get 133 million years, 197 million years, and 3.91 billion years. So, does this really help things? No, it doesn't. So, yeah. And enough of that. So, the main reason that this methodology is unsound is the same reason that when you look at water dripping into a cylinder, there's no way to know how long it's been dripping. You know, yeah, maybe you measure it in the present to be dripping at a rate of 50 milliliters per hour, and you observe that it's at 300 milliliters when you come across it, but you have to assume a ton of things for your dating method to be accurate. You know, you'd think, okay, 50 milliliters per hour, that would be 1 hour, 2, 3, 4, 5, 6 hours. But, again, you don't know that for sure, because you're assuming the drip rate has been constant this whole time. You're assuming the starting conditions. You're assuming you didn't begin with any water in the cylinder. And furthermore, you're assuming that no water has been added to or subtracted from the system since the beginning. And these are all assumptions that you can't verify, and that's why this methodology is so unsound. You don't have to write any of this down. It's the exact same thing you wrote down yesterday. But you can also kind of think of this like an hourglass, right? Fancy hourglass here. So, you know, radiometric dating is a lot like an hourglass. You have a certain amount of parent element you start with. Over time, it decays into non-radioactive daughter element, and based on that proportion, hopefully you could estimate how long it's been running. And that's something you can do for things that have half-lives and decay at quick rates like this, that you can actually confirm it's been decaying that way for a long period of time that you're looking at. But again, you have to assume lots and lots of things if you go to a time scale that's much larger than that. So if this was, you know, a gigantic hourglass and the sand is only going through at a very slow rate, you have to assume all sorts of things. You have to assume that none of the beads began in the bottom at the start. You have to assume that the decay rate is constant the whole time. You have to assume no beads have been added to or subtracted from the system. And I know I'm sounding like a broken record here, saying the same things over and over again, but I'm doing that because it's that important. This is the methodology that supposedly gives the Earth an age of 4.5 billion years and goes straight against the biblical version of history. I want to make sure that you realize that's not through good observable science that's done in the present. You get that number based on a lot of assumptions that you can't verify. So why doesn't it work? Again, the algebra and the arithmetic are very straightforward. They both depend on a number of assumptions about the history of the rock, none of which can be known to be true, as there was no eyewitness present throughout that history. Furthermore, when the measurement of ratios is done very near the time of formation of the rock, even the smallest amount of unexpected radiogenic daughter makes the calculations way, way, way off. From this slide, please write down the title and the first bullet point.
The first bullet point?
Yep. Title and first bullet point. So when I'm making these PowerPoints, I have to pick the background, I have to pick the font and everything and the sizing. I really like this font with this background. The only thing I don't like is, for whatever reason, anytime you put an apostrophe, it makes a gigantic space after it. So I don't know why that is. So if that bothers you, I apologize. There's actually no space in here when I'm typing this out. So it is what it is. But when we're dealing with these decay rates, again, we can't go back in time to look at the starting conditions. You can't go back supposedly 4.5 billion years to see if these rocks really started the way that they needed to for that dating method to be accurate. And there's no way for us to go back in time and know if anything has been added to or subtracted from the system. So you can't test hardly any of these assumptions. The one that you really can test, though, is the decay rate. And yet you can check to see if it actually changes over time. That's really the one that we can look at. And what we found is that decay rates of various elements actually change over time in conjunction with solar activity. And, it's not the sunspots themselves that cause this to happen. Sunspots are indicative of lots of magnetic activity going on the sun. And when there's lots of magnetic activity, it's giving off a lot more radiation for reasons that we talk about in astronomy. And that extra radiation that the Earth receives probably contributes to these different decay rates. In addition to that, indications from helium diffusion experiments are that there was a pulse of accelerated radioactive decay around the time of the flood. Of course, this is not the sort of thing you'll see the scientific community writing about. But as I mentioned in the last section, there are lots of wonderful Bible-believing Christian scientists that are doing research like this on stuff that actually happened in biblical history. And it's coming back with really interesting results. So while scientists who adhere to the billions of years perspective can construct explanations for the discrepancies between the real known ages and the incorrect radiometric ages, these are after-the-fact explanations, constructed when it becomes known that the measured results do not match with reality. When no reality check is possible, which is usually the case, it can't be known whether the measured ages are any more correct than the cases of examples that we discussed. Again, the examples that we talked about are not unique. I'm not just cherry-picking examples where the results came back poorly. They always come back poorly when we're testing the radiometric ages of rocks that we actually know the ages of. So, what about carbon dating? We're going to get into that today. So, carbon dating is fun. Carbon-14 is radioactive. Carbon comes in two versions that we're really familiar with here on Earth, carbon-14 and carbon-12. So carbon-12 is not radioactive. It doesn't decay. It doesn't change. It stays consistent over all time. But carbon-14 is its radioactive cousin. Because it's radioactive, it decays into something that isn't radioactive, and that's nitrogen-14. So carbon-14 combines with oxygen in the atmosphere to make carbon dioxide. Most of you probably know this if you've taken chemistry. Plants take this in, animals eat the plants, and then we eat the plants or animals, and we get carbon-14. We also inhale air, and that's the main way that we get carbon-12. So if you can imagine that you all came in here for lunch, and I decided to give the north side of the room all kinds of wonderful vegetables. And I gave the south side of the room all kinds of wonderful double and triple cheeseburgers. So whether you're eating vegetables or whether you're eating meat, you're going to get carbon-14 in your body regardless, because that carbon-14 is absorbed by plants, and if you eat the plants, you get the carbon-14. But if you're eating the meat, you're eating the meat of the animals which ate the plants. So regardless, you're going to get carbon-14 both ways inside your body. So you've got both carbon-12 and carbon-14 inside your body. Go ahead and write down the title and then the last bullet point here along with the 3 or 4 sub-points. So you're writing the title and then from here down. Bless you. All right, you're going to have to do a little bit of thinking here. I'm actually going to turn on the light for a moment so the folks at home can see this. So this is what's going on with carbon dating. Your carbon-12 remains constant after your death. The same amount of carbon-12 you have in your body when you die will be the same over the rest of, until you turn to dust. But carbon-14 is going to decay into nitrogen over that period of time. So the ratio of those two things, if you look at them, can hopefully give you an estimation of how long that person or animal has been dead. So let's just take a look at this. Let's say you see a ratio of lots of carbon-14 and not so much carbon-12 by comparison. Would that be something that has been dead recently or something that has been dead a long time? Recently, yeah. Maybe we just say this is young. Hasn't been deceased for all that long. And you can see how the rest of this would shake out. As time goes on, that carbon-14 disappears because it's changing into nitrogen-14. So when you get to the point where there's very little carbon-14, and by comparison there's lots of carbon-12, that object or thing or plant or animal has been dead for a long period of time because all that carbon-12 is now dominating that ratio there because the carbon-14 has all decayed into nitrogen-14. And I'll be coming back to this in the future here. Okay. Write down the last bullet point here, please.
Was the first 2 points the whole slide, or was it just the first 2 points?
For this one?
Yeah.
Just the last bullet point and the stuff underneath it here. So in order for carbon dating to be accurate over all time, we have to assume a lot of things, just like we had to assume a lot of things for when we were dealing with those much longer half-lives. So here we have to assume the ratio of carbon-12 to carbon-14 in the atmosphere at the time of death was the same as it is today. We have to assume there has been no change in the half-life of carbon-14 over that period of time. But again, carbon decays with a half-life of 5,730 years. which is great compared with the half-lives of billions of years of some of the other things we were talking about. So this method can't be as far off as some of the other ones. So we're headed in the right direction here in terms of precision and accuracy and reliability. And we'll see how that shakes out. And so in the same way that we want to test this method against some examples of things that we actually know the ages of, in the same way we did that with the rocks yesterday, we want to do that with something like that today. Before using any measurement, instrument, or technique, it's good practice to calibrate it against some known quantity to ensure accurate results. For radiometric dating techniques, the obvious approach is to use the technique to determine the ages of some rocks of known age. And in this case, because we're using carbon dating, we want to test something that isn't a rock. You can't really use carbon dating to test rocks, but things like wood, living creatures, stuff that breathes or takes in that carbon-12 and carbon-14, those are ideal for this methodology. And in 1949, Dr. Willard Libby developed this method and tested it against the age of a piece of wood from an ancient Egyptian royal barge. And this is the really good part about science. So when you're dealing with carbon dating, what this guy did is he used this method and he tested it against something that we knew the age of, an Egyptian royal barge, like a boat. And what we found from the carbon dating is that it matched up well with that date. And it's like, hallelujah, we actually used a radiometric dating technique and it backs up the age that we know the object is for a change. And this is good science. This is going back, testing your theory, and seeing if it checks out. This is not something that we've been able to do with those long age half-lives that we were talking about especially yesterday. So what this means is that carbon dating is probably accurate as far back as that date. So that's about 4,000 years ago. So in terms of the reliability of this method, we know that it's reliable back to about 4,000 years ago. That comes to about 500 years after Noah's flood. Radiocarbon dating has a very short half-life compared with radiometric dating. Obviously, I've already talked about the half-life of carbon dating there. It would take about 15.6 half-lives of carbon-14, which would come to about 90,000 years, to decay to the point where modern AMS machines can't detect it anymore. And this is the important part. That's why you got to write down this last bullet point right now. Write this down. This is going to kind of launch us into something that's even more interesting here. So just the very last bullet point.